In this chapter 5, we will learn about network layer. This one is about control plane. Previous chapter 4 was also network layer, but that was mainly for the data plane. Okay, here we look at the chapter goals. This chapter is mainly for understanding principles behind the network control plane. And we have traditional routing algorithm, thus we learn about that first. And after that, advanced one, newly introduced one, software-defined network controllers. And this one is common protocol, Internet Control Message Protocol, ICMP. This one is being used. Also, this one has been used for the ping command and the trace RT, trace route, trace RT or trace route command. This one has been used. And finally, network management. And their examples and implementation in the internet. And this routing information protocol, OSPF and the BGP, and new standard OpenFlow, ODL and ONOS controllers, ICMP, SNMP. We learn about them. This chapter is composed of 7 sub-chapters. First one is introduction. And next one is about routing protocols. And about the link state algorithm and distance vector algorithm. And this subchapter is explaining about the intra-autonomous system routing in the internet, open shortest path first. Okay, this is important routing information protocol. We'll learn about this. And next one is about the routing among the internet service providers. Between different autonomous systems, we are using some protocol that is BGP. And this is border gateway protocol. We learn this. And after that, we learn about software-defined network control plane. And the next one is ICMP, traditional ICMP, the Internet Control Message Protocol. We learn. For the IP version 6, as introduced already in the previous chapter, that is ICMP v6. But here we learn about ICMP for ICMP. This one is ICMP for IP version 4. We'll learn about this. And network management and the simple network management protocol. We'll learn this one. Finally, network layer functions. As we learned already, please recall 2 network layer functions: forwarding and routing. Forwarding is simply moving packets from router's input to appropriate route output. That is the data plane's functionality. And the routing, that is determining route taken by packets from source to destination. That is the control plane functionality. 2 approaches to structuring network control plane. Traditional approach. Per router control, for the traditional router, we are using this scheme. But newly introduced software-defined networking scheme, this one is, as we learned briefly, logically centralized control scheme we are using. Among 2 approaches to structuring network control plane, first one was per router control plane. This one is being introduced here. Individual routing algorithm components in each and every router. This one. Also this one. In each and every router interact with each other. They are interacting in control plane to compute forwarding tables. The main purpose of interaction is to compute this one, depending upon this routing algorithm. This one is traditional scheme, but to understand better about the control plane, we are discussing in this way. And now this is mainly for this computation of local forwarding table based on this per router control plane, based on this scheme. Okay, next one. This one is newly introduced one, logically centralized control plane using the software defined network concept. A distinct, typically remote controller, this one. Interact with local control agent, this one. This is called control agent in router to compute forwarding tables. Here, this one can be centralized logically. Thus, this one is called logically centralized control plane. And this one is interacting with this control agent to update this table. Let's look at the next subchapter. This one is about the routing protocols. There are two kinds, link state and distance vector. I simplified this one because to understand basic concept, instead of going through into the detailed information about that routing algorithm, this routing protocol goal is to determine good paths. Good path means we learn this least cost, fastest, or least congested in terms of computer network terminology. Think about good path in our journey or travel, shortest distance from this city to the next city, or the trip or traveling time, or if we are driving, then the toll gate fee, if that is least one, then depending upon our aspects, depending upon our metric, that will be different. This good, the meaning of goodness may be different. Okay, let's follow this one. From sending host to receiving host through network of routers, thus to determine this good path. That is the routing protocol's goal. Here, path means sequence of routers. In our computer networking infrastructure, we are using many routers. Packets will traverse in going from given initial source host to given final destination host. And the routing is very important. Thus, this is one of the top 10 networking challenges, like a congestion control, as we learned. This one is related to this algorithm, and to explain about that algorithm, even though we are not going through that algorithm in detail, this one is node. In our computer network, this one can be router, computer network node, Well, analogous example. In analogous example, this may be city for traveling salesman. The traveling salesman, he wants to find out the best way to arrive some destined city, or to travel all cities in shortest time or in least cost expense. Depending upon our goal, that may be different. In our analogous example, we can understand simply. But let's move to our computer network world. Then this one is networking device, especially router. Because we are going through this router to go to the final destination finally. And to analyze this one, some theory, that is graph theory, that is developed where? In the mathematical field by mathematician. And this notation, graph, is composed of this node and edge. This is node. And between them, this is edge. And N is the set of routers. Here we have U, V, W, that kind of routers. This is the set for that. And E is the edge. And in our computer terminology, that is links, communication links. There's UX, UV, UX, those are links. Graph abstraction is useful in other network context because this one is well developed by mathematicians. For example, P2P, where N is set of peers and E is set of TCP connections. We can apply this graph theory because that is well developed. And another one, to find out, we should look at this. This one is the cost of links from X to X dash. For example, WZ, that cost is 5. This is weighted edge. This is the weight or cost here. Cost could always be 1 or inversely related to bandwidth. Depending upon our metric, that cost will be different or inversely related to that congestion. Thus, in our real travel, this one may be there some distance like a kilometer, or if we are using some time, how long does it take from here to here, then maybe the unit may be hour. Thus, depending upon our metric, that may be changed. Thus, without any unit, this one can be used here, just the weight simply. That is the cost. Then if our goal is try to find the cost of path here, least cost from XP and X1, X2, and all of them, those are added up together, and this is the final destination. This is the source. Okay, let's look at this one. Key question is, what is the least cost path between U and Z? Here, this one is the starting node, and this one is the destination node. Destination. Then here, in this way, or in this way, okay, let's look at the other color here, like this, or like this. There may be many paths. Even though this is a simple one, we may have several different paths, and we can choose among them if we can find out least cost path. That is the solution. And how we can solve that? Our routing algorithm is used for that. This algorithm is calculating that cost, and that is finding out the least cost path. Then we can think some classification of the routing algorithm, because there may be some different kinds of classification. Let's look at this one. If our view is about the global or decentralized, centralized or decentralized, our main viewpoint is about that, then we can categorize in two groups like this: global algorithm or decentralized algorithm. Simply, we can divide into these two categories. If we are classifying these two categories, then all routers, this one, global is all routers have complete topology. That means this one has all information about the link cost information. And this is called the link state algorithm. Thus, this algorithm is using all information about that. Thus, this is called global. But think about if that node is so complicated and huge, so many, thus we cannot handle all of them together, then we can some distributed and some decentralized, just subset of that we can calculate. That is decentralized. Router knows physically connected neighbors. Thus, if this one is trying to find out some path, good path to arrive some destination, then this one is trying to calculate some information from the neighbors instead of all nodes in the world. Thus, this one is more realistic, because our network and the routers in the world is very huge. Router knows physically connected neighbors, link cost to neighbors, and iterative process of computation, exchange of information to neighbors. And during that iteration, this one is exchanging that information and finally trying to get that moment's best path, and then maybe change the next time. And thus, this one is continuously updating that information. This one is distance backed algorithm. Also, we can classify in other viewpoint whether that is changing slowly or it is being changed dynamically or quickly. Depending upon that, we can classify into two. One is static algorithm, another one is dynamic algorithm. Routes change slowly over time in this static algorithm, and in this dynamic algorithm, routes change more quickly, periodic update, and in response to link cost changes. That is being changed dynamically and quickly. Then that is called dynamic algorithm, routing algorithm. We learn about intra-autonomous system routing in the internet, and one of that example is OSPF protocol. This is routing information protocol and the intra-autonomous system routing information protocol. This autonomous system, we learn in detail about that. Okay, let's move. To make routing scalable, our routing study thus far idealized all routers identical, we are assuming. And network is flat. but actually the network is not flat, thus it is not true in practice. Because network nodes, the number of network nodes in the infrastructure, those are growing, that those have been growing so rapidly, thus that should be scalable. Thus we should consider this scalability of our routing algorithm. Scale is about this, with billions of destinations, and that information cannot be stored in routing tables. Thus, when we are considering the routing algorithm, we should think about that scalability. Routing table exchange would swamp links. Thus, due to that routing information exchange, the network may be very busy even for exchanging that information. And also there should be administrative autonomy. Internet, as we learned already, network of networks. These networks mean heterogeneous networks. That means complex and complicated. And in terms of administration, we should have some administrative autonomy in a certain section by a certain internet service provider. This one requires this one. Each network administrator may want to control routing in its own network to control that. In simple way, in terms of administration or management, that is called administrative autonomy by KT or LGU plus or SKT or Bell Atlantic in America, Southwestern Bell, Pacific Bell, depending upon that. Internet service provider, each one has its own administrative autonomy. Here, internet approach to scalable routing aggregate routers into regions known as we learned, autonomous system. This is called, in other words, or domains. Here we can divide into two groups. One is intra-AS routing and another one is inter-AS routing. This one is within that autonomous system. Inside, internally. Outside, externally. Inter-AS routing, we need different protocol for this. This is interior gateway protocol and this one is exterior gateway protocol we learn in next slide. Let's look at this one first. Routing among hosts, routers in same autonomous system, or autonomous system, or that is called network, or that same domain. All routers in autonomous system must learn same intra-domain protocol. Routers in different autonomous system can learn different intra-domain routing protocol. Think about this one is KT's and this one is LGU plus and this one is SK Telecom in Korea. Then between them, they need some that is internally intra, but externally inter. And this one is explaining about that. Routers in different autonomous system can learn different intra-domain routing protocol. Here, different intra-routing information protocol. Intra-domain routing information protocol. Routing protocol here. And the gateway here, we need this gateway to exchange properly. Gateway router at edge of its own autonomous system. This one is gateway router. This one is gateway router. Here, also here, here, here. At edge of its own autonomous system has links to routers in other autonomous system. Here, inter-AS routing. Between this autonomous system, routing among autonomous systems, gateways perform inter-domain routing as well as intra-domain routing. This one, okay, here, let's focus on that. This one can take care of that internal routing information protocol, routing protocol, and also external, that is intra-AS routing protocol. That is intra-domain inside and outside, inter-domain routing. Both of them. This one can take care of them. Okay, this one is, okay, I'll use this LED one. Interconnected autonomous systems. Okay, let's assume this one is autonomous system 1, and this one is autonomous system 2. This one is autonomous system 3. Then between them, we are using these gateways. And here, let's focus on this one, internal router. And this one is updating this porting table using this intra-AS routing algorithm, internal routing algorithm, as we learned, and this one is also using inter-AS routing algorithm. Both of them will be used to find out, to update that porting table. This porting table configured by both intra and inter-AS routing algorithm. Intra-AS routing determines entries for destinations within autonomous system. This one is only related to that intra. Intra means within that network autonomous system. And inter-AS and intra-AS determine entries for external destinations. From here to go to the other area, then we need to calculate based on this algorithm, inter-AS and intra-AS determine entries for external destinations. Because to go there, we should use that autonomous system. That packet datagram should be delivered in that way, in that direction. Also, we are sending our datagram to this client attached here, then that should be sent in this way. And this table should provide that information. And that table information, porting table, that should consider internal information and external information. And we'll learn anyhow in detail later. Okay, inter-AS tasks. Suppose router in AS1 receive datagram, this one. Receive datagram destined outside of AS1. This one receive datagram. And that is destined here. Some computer is attached here, and that is sending datagram to here, and that is destined to outside here or here. Router should forward packet to gateway router, but which one? This one, AS1, this one must learn which destinations are reachable. This one should have reachability information, and through that AS2 here, and still many other networks may be attached here, also here. Thus, through that AS1, AS3, which one can be reachable, and also through this AS2, which one can be reachable, we have some information that is called reachability information. And propagate this reachability information to all routers in AS1. That is the job of the Intra-AS Routing protocol. And the next slide will discuss a little more about that. First one, Intra-AS Routing. This one, also known as interior, that means internal gateway protocol. Short name, acronym is IGP. In advance, we are using this kind of IGP. Long time ago we used LEC, but we are using LEC version 2. Routing, this one is routing information protocol, basic one. At the beginning of this internet technology that has been used, but the maximum router we can go through, that is 15. Thus we cannot use this one anymore. Instead we are using this one. Okay, most common intra-AS routing protocols. Another one, OSPF, open shortest path first. This is related to the algorithm. Shortest path first. And also this one is very similar, almost identical to this one. Intermediate system to intermediate system protocol. Essentially same as OSPF. Another one, this one is proprietary by Cisco protocol. This one is Cisco's proprietary protocol until the year of 2016. But also this one is evolved, IGRP2. Okay, that is not, the name is EIGRP, enhanced, instead of this version number. Actually, this one is being used. This one is obsolete, not used anymore. This one is anyhow. This one is proprietary protocol, Cisco's proprietary protocol. The acronym is IGRP, and full name is here, Interior Gateway Routing Protocol. OSPF. This one is so important because this one is being used a lot. Open shortest path first. Usually routers has many different kinds of protocols, and the network manager can choose among them. This one, those are basic protocols, and depending upon the manufacturer, that may be different, but their okay, Cisco's router, then EIGRP will be, and also this one, OSPF, worldwide standard, and LEC version. Those are available, and network manager can use this one, following their company's policy in terms of that network management. This one is shortest path first. Open means worldwide standard. This is public available. This one is using link state algorithm. We learned about that classification in the previous slides. And link state packet dissemination, distribution, topology map at each node, and this one is using Dijkstra's algorithm. This Dijkstra's algorithm is introduced in the supplementary website. Video or clips are there, thus you can watch this one to understand better about this. Also, algorithm course or graph theory, you can see this Dijkstra algorithm. Actually, this Dijkstra, this one is the name of a person. He is mathematician and also he is computer scientist, Netherlands, Dutch. Around 1959, this Dijkstra, this scientist or mathematician, he was the computer programmer also. He worked there in some company. His birth year is 1930, and around this, probably 29, he developed this algorithm. And also he developed many computer-related algorithms, even GoTo, in other programming language. This is being used a lot. And many others he developed, and he's very famous. Thus that name is being used, Dijkstra's algorithm. This is being used for this link state packet dissemination and also this computation. Router uploads OSPF link state advertisement to all other routers in entire autonomous system. Carry in OSPF messages directly over Internet Protocol rather than TCP or UDP. This Internet Protocol is being used. And this link state for each attached link, that is called link state. Computer network, each link, that state. Here, intermediate system to intermediate system routing protocol, that is nearly identical to this OSPF. Okay, this one is introducing that the advanced features comparing to the basic routing information protocol, LEP, comparing to the LEP or LEP version 2, this one is providing these advanced features. Security. This one is providing security. All OSPF messages, that is so important, right? If that is being changed then wrong routing that is happening, thus that message is authenticated to prevent any malicious intrusion. This is security issue, and that is possible if we are using this OSPF. And multiple same cost passes, that is allowed, but in this LEP version, only one single pass is derived, that is being deserted finally. But this one is providing multiple paths. If that cost is same, depending upon that metric, then same passes. If that is same cost, then those multiple passes are recommended, that is allowed. And for each link in this OSPF, multiple cost metrics for different type of service. For example, satellite link cost set low for best effort type of service, but that is very high expensive for real-time type of service. In this case, the time is so urgent, important. Thus, satellite link is so slow, thus that is the high cost solution. But if that is using this best effort type of service, then it is not worrying about the speed, then this one will be good. Satellite link, that may be recommendable. Integrated uni and multicast, that is possible, that is supported using this OSPF. And also this multicast OSPF, short name is MOSPF, uses the same topology database as OSPF. And hierarchical OSPF in large domains, always we should think about the scalability. And these large domains, that is possible using this OSPF protocol. This is hierarchical OSPF. Okay, I'll use this one. Here, hierarchically, this one is area 1 and area 2, and this is area border routers, and this is backbone routers, and this one is boundary router, and this one is backbone router. And those are internal routers. Hierarchically, even though they are all routers, but different role hierarchically. Hierarchical OSPF, two-level hierarchy. Local area, okay, I'll use this one. And the backbone, as we just observed in the previous slide, link state advertisements only in area. And each node has detailed area information, area topology. Only know direction, shortest path to networks in other areas. And the area border routers, this one is summarizing distances to networks in own area and advertise to other area border routers. And backbone router, this one is learning OSPF, routing limited to backbone. And boundary routers role in this hierarchical OSPF, this one is connected to other autonomous systems. Okay, this one is the good point to wrap up, and we'll continue this discussion from this chapter about BGP, that is about routing protocol among the internet service providers.